Okay, at least it got rid of the. It doesn't have the part that wasn't any good anyway, and that's me talking. So I'm glad somebody was watching.
I see this little button that says "Start recording." I'm sort of should we get started?
Yes. So I'm glad you did that. Anyway, oh, I told you before we started. You know how I'm trying to remember. How do you like to do questions? Do you want us to interrupt you?
Okay. Nope. I'll ask for questions. What you can do is just take whatever questions the audience has. When I ask for questions, give me a couple. I'll answer more at the end. Anything that I don't get to, send it to me and I'll blog it eventually.
Good deal.
Been a little lax on my blog lately, but I'm sure I can fix that. And I apologize in advance for any loud meows that interrupt the podcast. My little cat has decided she's going to join me tonight. And she's sitting right underneath the microphone. All right, so indexes. Anything else from your side?
No, that's it.
My cat thinks I'm having a conversation with her. Meow, yes. Okay, on to indexing then. Okay, so decent introduction. I'm not going to bother introducing myself any further. Let's get straight on to indexing. What I'm going to talk about tonight, and it is tonight in South Africa, so if you're not in my time zone, good morning, afternoon, evening, or whatever it is, but it is night where I am. So what I'm going to talk about tonight is why we index. We're going to look at the index architecture, and then we're going to go through some guidelines for creating non-clustered indexes based on your queries and see just how to create good, useful, non-clustered indexes. And if we have time at the end, I'll gloss over some other index types, but I don't have time in this presentation to go into all the other index types that SQL Server has. Right, so why we index. And this is very important, and the order here is actually quite important. We index primarily to reduce the number of rows in consideration for a query as early as possible in that query's execution. In other words, we are creating indexes so that the query execution engine, if it needs to fetch 10 rows for a query, can fetch 10 rows, instead of having to fetch the entire table and filter it down to 10 rows. That is the primary main use for indexes that I'm going to talk about tonight. The second use, which is really? the second...
Gail, that was me. I'm sorry. I was trying to unmute myself. You're and I muted you. That's great. This is really good today. People have been. We can see your screen, the thing where it says "Start recording," the administrators panel.
Sorry.
Just hit that arrow. There you go. Okay.
That's better.
Sorry.
Okay. Whoops. That's better. Okay. I thought it was going to show everything but that. Never mind. Okay, so we're off to a great start tonight. Let's see if we can get a slightly more professional tonight. Okay, so the second reason you want to index is to support operations that require a sort. Now, this isn't necessarily order by, though that is the primary one. The other things that could require sorts are aggregations, more correctly the group by clause for the aggregations, merge joins, and windowing functions. All of those require a sort for rows, and all of them can benefit from indexes. The third reason, which I'm not going to talk about at all tonight, is to enforce uniqueness. This is more of a database design thing than a performance thing, and tonight I'm talking about performance. But if you are looking at the database design side, indexes are used to enforce uniqueness. Any unique constraint is actually enforced by an index. And this can be on a column, a set of columns, or even a subset of values in a column if you use filtered indexes. So let's keep those in mind as we go through this presentation. You'll see where the first two primarily get touched on again and again. All right. All right, so index architecture. I'm not going into a lot of detail here. This is not a 400-level session, but we'll touch on index architecture because it is important. SQL Server's indexes are B trees, balanced trees. The computer science grads in the audience are probably cursing me because that's not technically true, but it's close enough. They are not binary trees. If you ever run across a blog which explains SQL's indexes as a binary tree, close that window and run away fast. I have seen them. And doubly linked at all levels, every page has a link to every other page in the index. And we can see that here. So at the top of the index, we have the root page. Indexes will have a single root page. Sorry, indexes that have more than one page in them will have a single root page. Next one down is what we call the intermediate level. Not all indexes will have this. You only have this if the index has more than 2 levels. It's entirely likely for small indexes just to have the root and the leaf. And then at the bottom of the tree, we have the leaf level. The leaf level is where the actual data is for a clustered index, and the index rows for the non-clustered index. My mouse is not behaving very well tonight. Let me put that aside. It's actually not that important. I'll ignore that for now. So 3 operations that the query execution engine can do upon an index. The first one is a seek. The key part of a seek is that we are looking for a value. We are searching down the B tree to find either a row or the start or end of a range of rows. Either one is possible. Can you actually see my mouse pointer? So if I'm like this, can you see that?
Yeah, we can.
Okay. So a seek operation will start here. It's looking for a value and it moves down the tree. In fact, I actually have a better one in a sec. I'll show you those when we get to more detailed indexes. A scan of an index is when we're not looking for a value. We're either reading up or down the B tree. Sorry, we're reading potentially the entire leaf level. We might read a subset of it, but the thing here is we're not looking for a value. We're just going to read the entire index. And then lookups are single row seeks, always single row, and they are always against a clustered index or heap. You cannot do a lookup against a non-clustered index. I'm going to mostly ignore this. Density, selectivity, cardinality, that's for your reference. You can get this slide deck later and have a look at that. Predicates, when I talk about a predicate, it's an expression that evaluates true or false. Some ID equals 4 is a predicate. And a seek predicate is one that SQL can evaluate by traversing the tree. So a seek predicate is a subset of predicates. Right, theory aside, onto non-clustered indexes. Non-clustered indexes, now up until now I've been talking about indexes in general, B-tree indexes, and SQL's clustered indexes are B-trees, its non-clustered indexes are B-trees, its XML and spatial indexes are B-trees, and one of its index types on in-memory tables is also a B-tree. But for the rest of this presentation, I'm going to be talking specifically about non-clustered indexes. Actually, before I get into this, are there any useful questions on the initial stuff?
We have a couple of questions, but they're not really on the initial slides. Okay. They're more generic index questions.
I will move on, and I'll take some more questions in a bit. Right, so a non-clustered index is always considered to be a secondary structure. It is always separate from the table that is created upon. Hence, non-clustered indexes are always a form of duplicate data. So you need to consider when you're creating non-clustered indexes, you are duplicating the data in the table, at least partially. They are always in sync with the table. There is no case, other than severe database corruption, where an index contains different data to the table itself. They are updated, inserted, deleted as part of the operation which affects the table itself. With the sole exception of filtered indexes, there is always one row in the index for every row in the table. You don't have indexes on parts of the table, you don't have indexes on only unique rows. The rows in the index match one-to-one the rows in the table. As I said, the exception here is filtered indexes, which we will talk about at the end. And every index row has a pointer to the actual data for that row. The pointer is the clustered index key if the table has a clustered index. The pointer is the RID if the table's a heap. That's 8 bytes, file ID, page number, slot index. Keep in mind what this means is that if you make the clustered index key very large, you're adding that overhead to every single non-clustered index you have. It's something to keep in mind when you're designing your clustered index. Come on, behave. All right, so this is a better depiction of a non-clustered index. If I was going to be doing a seek operation on this index, seeking for whatever my first column, we'll call it column A, seeking for column A equals F. The way it works is we start here. Now, F is greater than A, but less than K, so it must be on this half of the tree. The index is logically ordered by its key. So we start with A, we go down towards Z. So if we're looking for F, it must be this way. Now, it's not on this page, it's not on this page, it's not on this page, it's probably on this page. Well, it has to be, because this one starts with I, and I is greater than F. So if we're looking for the values F, we're going to follow this pointer down, and we're going to find these two rows. Now, let's assume we're doing a two-column seek operation. We're looking for E9. Well, we start here, same thing. It's greater than A, less than K, so here. We ignore this page because E1, E8, we're looking for E9. We don't need to look on this page because there's no way that E9 can be on this page because it starts at 1 and the next page starts at 8. So the only possible page E9 can be on is again this one, and we find it here. The key point here is that if SQL is doing a seek on two columns and there's an index designed correctly, it's a two-column seek operation. We didn't have to read all of the values of E and then filter out the ones we didn't want. We went straight to the row that had the value that we were looking for. Right, so given that, let's look at some guidelines for non-clustered indexes. Non-clustered indexes, in general, you want them to be selective or covering or both. Now, selective, I did touch on the definition earlier, I didn't go into detail on it. Selective for an index means that queries against it return a small number of rows. So it's not necessarily about the data type or the data, it's about the types of queries. If you're using non-clustered indexes, you want to design them so that they return small numbers of rows when used in queries. The alternative is that the index is covering. Now, a covering index is one that contains all of the columns necessary for the query. So selective and covering are both about the index and the query. We cannot look at an index alone and say that it's selective or covering. We have to look at it in conjunction with the query. And this is one very important aspect of indexes. You can't design indexes without knowing the queries that run against the tables. You must know both in order to index properly. So, covering. If my query is looking for column 1, column 2, column 3, wherever, in the select, in the join, in the where, in the group by, doesn't matter where in the index, in the query they are. A covering index is one that contains column 1, column 2, and column 3 somewhere in it, in either the key or the include. The reason that you want indexes to be selective or covering is the lookups. If an index is not covering, if, for example, our query needs column 1, column 2, column 3, but my index only has column 1 and column 2 in it, the query execution engine has to get column 3 from somewhere. And where it gets it from is the clustered index. And how it gets it is those lookups. And those lookups are single row seeks. And those are expensive when you start getting towards larger row counts because you're executing them, a lot of them. You can imagine looking up 1,000 different rows. That's 1,000 seeks against my clustered index. That gets expensive. And it turns out SQL does not like doing lookups on large percentages of the table. And by large here, I mean roughly 0.5% of the table or larger. At that point, if it has to do lookups on larger numbers of rows than that, it'll typically flip to a clustered index scan, which is typically not very efficient, and you don't really want that. Hence, selective or covering, or both. Wide indexes are much more useful than narrow indexes when it comes to a non-clustered index. Now, the rules are different for clusters. This is a non-clustered index. What this means is that the indexing strategy, and I use that term in quotes and very sarcastically, of putting single column non-clustered indexes on most of the columns in my table is completely useless because SQL's not going to use them very much. So when you are indexing, you want wider indexes in general. You need them to be selective or covering, or both. Start by looking at your most frequently run, most important queries and creating covering indexes for them. And then worry about the less important queries later. Consider indexes to support order by and group by. That's your sort. But this is not the primary goal of an index. The primary goal is reducing the row count. The order by and group by is later. And to make your index covering, use the include clause for columns which are in the select clause but not in the from or the join. Or not in the from or the where clause. So before I go into details of indexing, are there any questions on those?
Oh yeah, we have questions.
I bet you have questions.
We've got one saying, sorry, when the key column is the last name, would the actual last name in the non-clustered index be contained in the index and the table, or is it only in one?
The index is duplicate. The index is a secondary structure to the table, and it's duplicate. So if you have a table with 10 columns, and you create a non-clustered index on 3 of those columns, the table has 10 columns, the non-clustered index has 3. Those 3 are completely duplicated. That's why you need to be careful about the number of indexes you create. You are duplicating data.
Okay,
and
interesting.
it gets large.
We have a question from Slack saying, it's a kind of general question, how wide is too wide on a non-clustered index?
I am going to solely answer that one with it depends and move on. That one needs a blog post or 10 to answer. Yeah, it's a very much it depends. For example, if I've got a data warehouse, I might be absolutely happy with indexes that are 20 columns wide. If I've got an OLTP system, I'll be twitching at about 4. Very, very dependent on what you're actually doing.
Okay. And I suppose the final question is, somebody asked, does the IAM pages gradually grow with indexes?
IAM pages, no, I'm not talking about SQL internals. IAM pages are firstly 8 kilobytes, they're pages. They are maps to where the index pages are, so the more pages you have, the more IAM pages you're going to need. That's fairly obvious. An IAM page maps 2 gigabytes of the file. If your index is in multiple places, you need more IAM pages. That's not really a concern, though. It's 1 for potentially 2 gigs. That IAM pages are not a concern.
That's perfect. There is more, but I'll leave you back to your great session and come back to you again.
Okay, I will get on with these. This smells like several blog posts later. I actually have a lot of this in blog posts, so it might be just a case of here are the links. All right, so let's look at indexing for equality. And by this, I mean we've got a situation where we've got a where clause, column 1 equals something, and column 2 equals something else, and column 3 equals a third thing. And I don't know if I actually have Management Studio. I do indeed. Awesome. So that would be a 2-column equality predicate. Yes, I know I don't have a whole query about it, but that's fine. We don't need that. When you are looking at indexing equality predicates, the order of the columns in the index don't matter very much. If I've got this as a predicate, this can use an index on column A, comma column B. Indentation's gone to hell. It can equally easily use an index the other way around. And for this particular query, there's nothing in the where clause which says which one of these to use. Where you start needing to decide on order of columns when you're supporting equality matches is when you're trying to support multiple queries with a single index. And this is really something you should be trying to do. Your goal with indexing is to support as many queries as possible with as few indexes as possible. I could easily custom build an index for every single query I have, but that's going to get very inefficient very quickly. If this is an OLTP system, it will kill the inserts, and the space usage will be ridiculous. So let's say I've got this query, and I also have another query that is just that.
I'm very sorry, Gail. We've had a couple of comments. Could you zoom in for a second on that code?
Let me fix. I can do better than zooming in. How's that?
Brilliant, thank you.
Just a hint for people, Management Studio has a text zoom in the bottom left corner. It is awesome. That should be large enough for everybody, even if they're watching at the back of a room. Okay, so we've got two queries, and what's in the select is utterly irrelevant. One query is filtering on column A and column B combined. One is filtering only on column B. Now, going back to our index architecture, SQL can only seek on an index if it's seeking on a left-based subset of that index. If we look at this index tree, I can easily find column 1 equals, I don't know, O, but I cannot easily find column 2 equals 7. Because column 1 equals O is going to be found here. It's got to be on this page. It's got nowhere else it can possibly be because N and S. Column 2 equals 7. Well, there's one here and one here and one here, and who knows how many more on the pages that I didn't bother writing out in full. So if SQL is seeking, it can seek in this case on column 1 or on the combination of column 1 and column 2. But if it has to filter for column 2 only, it is doing a scan. It cannot seek. It's a non-sargable predicate because the index does not support that seek order. And so if I'm trying to support these two queries with one index, I only actually have one index order option. This is not suitable because while this one fully supports my first query, my second query has to scan. So that's not ideal. So I want this one instead. This one allows both of my queries to seek. I don't have to scan. Now, of course, if I've got another query, I can't support all three of those with one index. It's absolutely impossible to do that. What I would do in this case is either construct two indexes, or if one of these queries is not very important, not run very often, not particularly urgent, I'll actually let it scan. It might not be that bad. So, back to my slides. Very, very important, if there's one thing you take away from this presentation, index seeks are only possible on a left-based subset of the index key. Memorize that. It is the absolute key to creating indexes. Absolutely no pun intended by that. Before we carry on, because things get more complicated from here, are there a couple of questions on this?
There is a couple of questions, but you've actually answered them in the presentation, so I'm just replying now.
Okay, cool. Moving on then. Indexing for inequalities. Let's go back to my index architecture. If I'm looking for column 1 greater than F and column 2 equals 6, this column order is not particularly appropriate, because column 1 greater than F means I've got to start here and read all of this portion of the index and then throw away anything that was not equal to 6. So I've got to basically do a partial scan. I've got to read half my index and throw away a good portion of my rows. If I wanted to be able to do that, column 2 equals 6 and column 1 greater than F, I'd probably want to flip my index key order around so that my numeric column is first. The reason I say that, let's say we're looking for column 1 equals E and column 2 less than 3. Well, column 1 equals E is easy, it's here, and less than 3 means I'd read 3 rows. I read 3 rows and only the 3 rows that I needed, as opposed to reading half the index and throwing away a bunch of rows I don't need. Remember, the point of an index is to reduce the number of rows in consideration for the query as early as possible. If I'm doing an equality on column 1 and an inequality on column 2, this index order is appropriate. If I'm doing the other way around, this index column order is not appropriate. I hope that makes sense. Basically, what I mean by that is if I have that as a where clause, this is the most appropriate index key order. Because if I flip them around, I'm going to have to scan part of the table and throw away a whole bunch of rows. I know that's probably complicated. I like whiteboards when I'm doing this, and I don't have whiteboards here. Any quick questions on that?
Sorry, Gail, I have myself on mute. No, not quite on that exactly.
Okay, I'm going to assume everybody understood that perfectly, which is awesome. Let's get a little bit more complicated. No, not my properties. Geez, my keyboard's really going crazy today. What the hell? Right, so let's actually say I've got 3 columns. Right, this is a nasty one because there is no efficient way to index this properly. Now, column B I still want first because it's my equality. Equalities before inequalities when you're doing index design. This, by the way, is why the missing index DMV always gives you the equality columns and the inequality columns as separate lists. It's so that you can put the equality columns first. But whatever I put as my next column, I'm going to still have inefficiencies. I'm going to have to filter. Sorry, I'm going to have to do a seek, fetch a bunch of rows, and then throw rows away that don't match the other criteria. And when I'm looking at this, what determines the order here, whether it's A then C or C then A, is not this query, because this query doesn't tell me anything. It's going to be potentially other queries in my database. Do I have any queries that filter on, say, A and B only? Do I have any that filter on B and C only? Do I have any that filter equality on B, equality on A, inequality on C? That's going to determine more what my index column order is, more than this query alone. If I have nothing else to determine what order I put my columns in, then I'm going to look for which one of these reduces the row count the most. That doesn't mean the one that has the most unique column. We've got inequalities here. If this is a number, an integer that starts at 0 and goes to 10 million, and I'm looking for greater than 10, this is not going to filter a lot of my data out. So I would look for whichever of these filters my data best and put that first. Again, going back to our fundamental requirement, the index should allow the execution engine to reduce the rows that it is considering the most as early as possible. We want to fetch as few rows as possible from the table to do additional processing on. All right, that's inequalities. Sorts and group bys. This has got nothing to do with seeks. This has got to do with ordering, because my index is logically ordered by its key columns. It's logically ordered A to Z, and within each letter 1 to 9. And so I can use an index to support an order by. If I'm, say, doing select star from this table, order by column 1, this index provides that order. And so the execution engine might be able to use this index to fetch the data ordered rather than have to do an expensive sort operation. Similarly, if I'm, for example, saying, give me the sum of column 2 grouped by column 1, it can just read this index. My data is already grouped because it's ordered by those columns. And so we don't need to do expensive hash aggregates. We don't need to do expensive sort operations to get our aggregations because the data is already sorted in the correct order. I will say that this is less important than the filters. The primary use of an index is to filter. The secondary use is to provide a logical sort order. So if you can't do this, don't worry too much. Having an index that lets the execution engine filter the rows more efficiently is far more important than an index that allows you to sort and group by more efficiently. Definitely consider it after supporting the where clause. Don't assume you can always do it, but if you can, it can be very beneficial. So it is something to consider. It's not necessarily something that you're going to get all the time. Joins. This is quick, so I'll go through this one. 3 join types in SQL Server. We've got the loop join, the merge join, and the hash join. I'll take them backwards. The hash join doesn't care about indexes. It doesn't use them. The hash join fetches the rows from both inputs, hashes one into a hash table, hashes the other one into a probe, and does its join that way. When you've got hash joins, the only thing that the indexes could be used for is the where clause, not the join. Merge, well, see the previous point about sorting and aggregating, because merge requires that the two inputs are both sorted on the join columns. SQL does not like sorting large amounts of data for no reason, so merge is something you're only likely to see if the data is already sorted or if there's an index that allows that sort to be avoided, essentially. Hence, if you have an index on the join column, you might get a merge join instead of a hash. That might be a good thing, but again, look at the where clause first. Filtering is far more important. The loop join is the one that can benefit on an index. And I say on the inner table. Which one is the inner table? That's a big it depends. Let me go find a query quickly. I have all right, which table is the inner and the outer? I cannot tell that from looking at the query. I have to go and look at the execution plan. And yes, I've got a nested loop join as I expected. the position of the tables in the execution plan tells you which one's the inner and the outer. In this case, stations is the outer table and star systems is the inner table. And you'll note we have a nested loop join with an index seek operation. You'll also note I have no where clause on this query. So this is a seek on the join. When you have nested loop joins, the join can benefit on an index on the inner table on the join column. Keep in mind, however, that SQL is unlikely to use two indexes on the same table for the same query, with one exception that we'll get to, I think, on the next slide, if I remember to put it back in. So you probably want here a multi-column index on to satisfy the where clause first, and then the join columns. Definitely something you consider doing after the where clause. It's certainly worth looking at, especially if you want or have nested loop joins. You're not likely to get nested loop joins if there isn't a useful index on the inner table. SQL's more likely to take a hash join because it doesn't like scanning the inner table repeatedly. And I have indeed forgotten in my slide on indexing for ORs, so I will just do this one in the query window. Right, we've been talking so far about ANDs. And when you've got ANDs, every additional predicate reduces the row count further because they apply more and more and more conditions. OR is exactly the opposite. And OR, every additional predicate expands the row count because this is a, trying to think of the correct official term, disjunct I think it is. Each of these is concatenated in. So if I add col C, by doing this I've probably added more rows into my result set. As such, this cannot use a single index because how could we use a single index for this? These are two separate predicates that have to be applied, and the resulting rows from this are the ones that meet either of them, not both of them. And so the same rule as we saw in the equality earlier does not apply here. What you need for all predicates is multiple indexes. To satisfy this, because it's an OR, I need two indexes, one on column A and one on column B. If I have the index that I created earlier, what you'll get out of this is a scan, because while this can be satisfied using this index, this can't. That would have to be an index scan, and so you get a single index scan for this OR. So if you're indexing for OR predicates, you need multiple indexes, one for each of the OR clauses. Right, so to make this a little bit more complicated, let me add some more stuff in here. Right, so now I've got a mixture of ANDs and ORs. I will spare you the relational algebra necessary to tear this one apart, but what you essentially need for this is two indexes again, like that. Of course, I could flip the order around here. That's perfectly valid as well, because what this equates to when you go do some relational manipulation on it, never type in demos, never type in demos, never type in demos. Going a bit off the screen, but I think you can see that. So I've got two predicates with an OR, and so I need an index on that, and I need an index on that, and this is a standard equality match that we've seen earlier, and so I can flip the order around, and I probably would so that I have a decent spread for my indexes. All right, that's a very, very quick look at indexing for various query options. And I think I'm nearly out of time, so filtered indexes will be quick, but I'll take a couple more questions on any of this indexing stuff that I've talked about so far.
Well, you've got 10 questions, but I might just keep it down to 3 if I can. Someone does want to know if your interstellar travel database is freely available.
They want my interstellar transport. Yes, actually it is. I will, however, say, oh, geez, come on. Yes, I have the interstellar transport up. There's no sample data yet. So what I've done for this is throw Redgate's SQL data generator at it and generate some garbage data. Bookmark this page. I will eventually get this thing finished and get some good sample data and get more queries. I basically wanted a sample database that was fun to work with. And I'm a sci-fi fan, so interstellar transport. Okay, so that's my database.
Okay. You did mention before that indexing is about the queries that are run. Somebody wanted to know, is there any DMVs to capture that information, or would that be a manual research thing?
sysdm exec query stats cross-applied to dm exec SQL text. That will catch whatever's in the cache at the moment. Otherwise, extended events, and if you run SQL 2016, query store, query store, query store. And if you're not on SQL 2016, why the hell not? Because query store. And seriously, query store is absolutely awesome. That will do it without any problem. Other than that, extended events, profiler if you're on 2008 R2 or before, and if you are, my condolences. Otherwise, the DMVs will do a partial job. They don't do a full job because it requires that the plan is still in cache. You are going to be analyzing your workload. You can also use the missing index DMVs as a place to start, but it's not a good place to finish. Don't take what the missing index DMVs says and create it without thinking, but it's a good place to look and start thinking about what indexes do my queries actually need. But I'd start with extended events and the plan cache or query store.
Okay. Final one before I let you get back to it. Someone just wants to know if you're joining on 2 tables and you group by a column in each table, would you know how the order by or group by work, or does it depend again?
You're going to have to look at the execution plan of that, because it's really going to depend on a lot of things, including what constraints SQL knows about on those tables, what type of join. Go look at the execution plan. The execution plan will tell you how the queries run. From that, you should be able to work out what you need to index to support those 2 aggregations. Because it might do the aggregations after the join, it might do them before. But you're going to have to look at the execution plan. I cannot answer that question.
That's fair enough, and I won't take more of your time and let you get back to it.
Filtered indexes. I think this is roughly it. Yeah, almost. Okay, so filtered indexes are the sole time that you have an index that is not the entire table. An index that is a subset of the rows in the table. This is very, very simple. You create an index and you put a where clause on it. And I may as well, no, not that one. Let me go, sorry. Let's see. Whatever. That kind of thing. You put a where clause on a non-clustered index. Has to be non-clustered. You can't filter a clustered index. For obvious reasons, the clustered index is the table. It can't be filtered. Some things to keep in mind, this where clause has to be simple. You cannot do complicated filters. You cannot do ORs in it. It's got to be very, very simple, and you probably want to keep it to 1 predicate. Mostly because how it matches back to the queries. To be usable for a query, the filter on the query must match the filter on the index or be an obvious subset of the filter on the or be an obvious subset of the filter on the index. Yes, that was horrendously complicated. So this non-clustered index, is it roots? No, roots. Roots. Div type in demos. That might work. You note I didn't. Yeah, I did put a column. Okay. So this could use the non-clustered index. This could use the non-clustered index because this is definitely a subset of that. But that won't. Because it can't, while these are, at least as far as I'm aware, logically equivalent, if my maths is correct, which it may not be, it is kind of late, they are not considered to be easy to match. So you've got to be very careful with your predicates. That's also fine. That should also work. This does not work because we can't tell what this is. So as soon as you parameterize your query, it can no longer use your filtered indexes. And that's actually the biggest problem. If SQL auto-parameterizes your query, you can't use the filtered index because I don't know what that is. To be honest, while I like this, it's got a few too many bugs in it for me to use it a lot. The main time I use filtered indexes is actually for uniqueness. Anyone that was paying attention when I talked about uniqueness at the beginning might have noticed that I said indexes are used to enforce uniqueness on a column, set of columns, or subset of values in a column. Subset of values in a column is what you use the filtered index for. Let's see, index. Let's see what have I got here that's actually useful. This is going to be very contrived and very stupid and very, very strange. Right, what that does is require, actually, let's do a more obvious one. Invoice number where, this is probably something most people have encountered, a requirement that a column is unique or null. The problem with that is you can't use a unique index for it because as far as a unique index is concerned, null does equal to null. So a unique index allows one and only one null, which is probably not what you want. So if you want a column which is null, optional column, and if the value is specified, it must be unique, you do it with a filtered index like this. Filter index, I will help if I actually put the unique constraint here. Right, like this. Unique index on invoice number where the invoice number is not null. If it is specified, it is unique, but it's optional. So that's one of the main uses for filtered indexes that I do like. Other than that, the parameterization catches you way too often for my liking, and it's got a few too many bugs in it. But you may find cases where this is useful. I've used them a few times recently to tweak very important, to tune very important queries, and they proved quite useful. All right, in the include columns, I mentioned earlier you use include columns for columns that are in the select, not in the where or the from. This is used for covering indexes. Columns in the include do not count towards the 16-column 900-byte limit to the index key, and you can put anything into the include column other than the old lob data types. So it is worth considering using the include columns to cover your index. It's better than the index keys. Okay, and that is roughly that. Now, I'm not going to talk about column stores or hash indexes or anything else because, quite frankly, I don't have time. And while I'd love to sit here for another 2 hours and talk, I'm pretty sure everyone else has somewhere else to be. So we've got a couple minutes left, I think. I'll take a couple more questions if you have some fun ones.
I have like 9 or 10 there. I think this is the most questions I've ever had. We've got a fun one here. Can you use a function on the where clause and still use an index?
Can you use a function on the where clause, providing you use it on the constants or variables, not on the column? No, basically. any function on a column in a where clause will prevent index usage because the index is on the column, it's not on the function of a column. There are a couple of exceptions here, but they are exceptions and should not be depended on. If you absolutely need to do this, what you'd have to do is create a computed column, which is function of column, and index that and use that in your where clause. I'd suggest just avoid it as much as you can and compute a column for the cases where you cannot avoid it.
That's fair enough. We've got an interesting enough one here. One of the audience members has a customer table with an identity column and a customer name. The identity column is int, the customer name is varchar 30. So because the customer name is used in the queries most often, would that be a good clustered index key candidate?
Clustered index, probably not. Yeah, gonna have to look at this one. It's going to depend how often I change the customer table, as in insert, update, delete it. If the customer table is fairly static, it might be okay. Or I might just put a non-clustered index on it. Here's the question. If you filter on the customer name, how many rows are you likely to be returning? If 1 or 2, that's fine for a non-covering, non-clustered index. It's actually what they're really good at. If you're going to be returning 3/4 of the table, I'd be interested to see your customer table design firstly. And that's probably more where you want the clustered index because it's covering by default. Probably not. Also look at your joins. If the customer table is frequently joined to on the customer ID, you might want the clustered index there because of the join.
Okay. There was an interesting one, but unfortunately the audience member has left, so I'm going to use a different one. Yeah, if you have a non-clustered and a clustered index on the same column on the same table, which index query plan would get used?
Both very happily. Because some queries don't need all the columns, and for those the optimizer will pick the smaller index, and for some you need most of the columns, and for those the optimizer will pick the clustered index, and it's going to depend on the row count. I will say that's probably a useless index though, it's redundant. The optimizer will use it, but whether it needs to be there is another matter. You're probably saving a few microseconds using the non-clustered index over the cluster, but paying the overhead for a full new index. So I don't like seeing those. If you've got a really, really time-sensitive query, it might be a good idea. If you've got a really wide table, it might be an idea. In general, it's redundant and not necessary. But both of them will very happily be used. Here's a fun fact. If you've got 2 absolutely identical indexes on a table, both of them will be used. So that's just how the optimizer works.
You know what, Gail, questions are still coming in, so I'm going to ask one final one and let you go. There is a lot of thank yous coming through and lots of information being learned, so they are very appreciative. But I guess the final question. Sorry?
Drop me the rest of the questions by email, and I'll get around to blogging them one of these weeks.
Okay.
Probably one
so
of
I guess
them this year.
Final question is, do you know what the efficiency is like if you have a binary column in the first position of an index? Or have you ever seen it before?
I'm going to assume the guy means a bit. Most of the time I see bit columns, it's things like is deleted, is active, where you're always filtering for one of the values, not the other one. You're always filtering for is active equals 1, you're never filtering for is active equals 0. In that case, consider a filtered index, because you don't need to consider most of the table. Test it out. It's not necessarily a problem. It might hurt you on the inserts, it might not. I wouldn't put an index on the bit column alone. The bit column and some other columns might be okay, but I'd probably for that look at actually filtering the index on that bit column, because I probably don't actually care what its value is. I'm just using it to exclude rows that I don't care about.
Okay, yeah. No, what we'll do now is we'll grab the rest of the questions, send them on to you, because they're literally still coming in.
Cool. Oh, thank you very much. That was fun.
No, thank you, Gail. That was great. I love the way you do this. You ought to do something like this on Pluralsight with beginning indexing and sort of intermediate indexing. I know you're doing stuff on Pluralsight now, so I just thought that that would be good.
I'll give you let's see, where was I can probably get this better. It's Paul's. Oh, jeez. Yes, that one. Where is his most recent one of his recent blog posts? Nope. Oh, recent. I'm looking back to January, so this might take a while. So let me try and. I know it was from this year, probably January or February. I'll give you something to look forward to. Nope, not that one. Sorry, I know it's... Okay, so Paul actually posted either December or January the Pluralsight, the SQL skills plans for Pluralsight this year, and they're doing an indexing. Kimberly's doing indexing, so that's going to be, yeah, Kimberly and indexing. So that should be something to look forward to. It's Kimberly and it's indexing. So I don't know why else you'd be looking for anything. I mean, it's Kimberly and it's indexing.
You ought to do one on Query Store.
I am finished. Yes, I have actually finished one on Query Store.
Good deal.
Oh, there we go. There you go. Course in the works for 2017, indexing performance. I can only imagine that's Kimberly doing it because no one else is going to do that. So somebody else is already doing it. So I'll work on other things.
Okay. Well, I really appreciate it. You did a great job. I love the way you explain things. That's why you're going to be really good on Pluralsight. So we really like that product. So.
Good.
Next month, or actually next week, we've got one with DBA Fundamentals Down Under, basically going through the entire process for HADR design and implementation. The next week after that, we have Joy D'Antonio with all of the new features that 2016 Service Pack 1 gives you, so you don't have to buy Enterprise, the limitations and the things you can do with it. And I found the information on Jess Borland, which I love her sessions. She always has very unique sessions. She's doing one with the professional development site. Busy is a 4-letter word. We're all busy. We need to check this one out. That is the 14th of next week, Wednesday. Thank you, Gail, and I really appreciate it. Great job, Shane, and we'll see you. At least we will see you the 20th. Thanks. Bye.
Thank you.
I'm glad you reminded me to to do the recording.